Friends, welcome back. In this tutorial we will study about deadlock detection algorithm, which is applicable in a system which is having several instances of a resource type. In previous tutorial we studied how we can detect deadlock by using wait for graph. That algorithm which employed wait for graph for detecting the deadlock, that was applicable only in a system which is having a single instance of a resource type, right? But this that wait for graph algorithm is not applicable in a system where there are several instances of a resource type. But this algorithm which we are going to study in this tutorial, that is applicable here, where there are several instances of a resource type. Now suppose there are n processes, p1, p2, p3, so on up to pn, and there are m resource types in the system, r1, r2, r3, so on up to rn, right? So to implement this algorithm we need to keep some data structures as we kept in Banker's algorithm. So one is available, so this is a vector of length m, and it indicates the number of available resources of each type. So if in this vector available at index I the value is k, it means there are k instances of resource type ri. Now another is allocation. What is this allocation? It is an n cross m matrix, and it defines the number of resources of each type which are currently allocated to each process. If the entry at ith row and jth column in allocation matrix is k, it means k instances of resource type rj have been allocated to process pi, right? So the ith row of this allocation matrix specifies the number of instances of resource type allocated to process pi, right? So each row of this allocation matrix is considered as vector. Now another is request, right? It is also an n cross m matrix, and it indicates the current request of each process. If in this matrix at ith row and jth column the value is k, then it means the process pi is requesting k more instances of resource type rj, right? So the ith row of this matrix request, right? Ith row of request matrix, it specifies the current request of process pi, right? So each row of this matrix is also considered as a vector. Now we will study this algorithm, right? So how deadlock can be detected by this algorithm. So first we will consider that there is a system, and in that system there are n processes, p1, p2, p3, p4, and so on up to pn, and there are m resource types, r1, r2, r3, and so on up to rm. So the first step of this algorithm is we will consider two vectors, work and finish. Work is a vector of length m, and finish is a vector of length n, because there are n processes, right? And work is a vector of length m because there are m resource types. Now we have to initialize the values of work and finish. So we will initialize work by assigning it to the value of vector available. And what happens in this finish vector, right? So at we will check all the indexes of a finish vector, right? So what happens if there is some process pi, right, and to that process no resources are allocated, right? Then what we will do, suppose there is some process pi, and to that process pi no resources are allocated, then what we will do in vector finish at index I, right, we will set the value true, right? Otherwise if there are processes to which resources are allocated, then what will happen, whatever the index is there corresponding to these processes, at that indexes in the finish vector we will set the value false, right? So if the resources are allocated to the process pi, then at index I in vector finish we will set the value false. If no resources are allocated to the process pi, right, then at index I in the finish vector we will set the value true, right? This we have to do for all values of I from 1 to n, because there are n processes in the system. Now the second step. In second step we have to find an index such that value is stored at index I in vector finish is false, right? And ith row of request matrix which specifies the request of process pi is less than or equal to work, right? If no such I exists, then we will go to step 4. If in the system we do not find any index I like this which satisfies these two conditions, then we will go to step 4. Now what happens in step 4? In step 4 we check if in vector finish at any index I, if value false is there, right, then the system is in a deadlock state, right? It means we need to check all the values in finish vector, right, at indexes from 1 to n, right? So we need to check this values which are stored in finish vector at indexes I, where value of I is from 1 to n, right? Because there are n processes in the system, right? So if somewhere we find the value is false, then it means the system is in deadlock state, right? Now suppose if we find some index I in step 2 which satisfy these two conditions, then what we will do, we will go to step 3. We will not go to step 4. In step 3 what happens, we will update the value of work vector. To work vector we will add the ith row of allocation matrix, right? Ith row of allocation matrix specifies the resources which are allocated to process pi, right? And then what we do, we will set the value at ith index in finish vector to true, right? And again then after that we will go to step 2, right? Again we will find an index I which will satisfy these two conditions, right? If we find an index I which satisfies these two conditions, we will go to step 3. Otherwise we will go to step 4, right? It will be clear after this example. Now consider that there are 5 processes in the system: P1, P2, P3, P4, P5. This is the allocation matrix, this is the request matrix, and this is the available vector. And here you can see that there are 3 resource types A, B, C, right? Process P1 is allocated 0 instance of resource type A, and process P1 is allocated 1 instance of resource type B and 0 instance of resource type C, right? In available vector you can see that there is no available free instance of resource type A, no free available instance of resource type B, right? And no instance of resource type C is available, right? Now these matrices are given to us: allocation matrix, request matrix, and this available vector is given to us. And here there are 5 processes and 3 resource types A, B, C, right? And now we have to, what we have to do, we have to apply this deadlock detection algorithm, right, which will find out whether the deadlock exists in this system or not. So what is the first step? First step is that we will take 2 vectors work, right? Work vector will be of length 3 because there are 3 resource types, and we will take a finish vector, right? Finish vector will be of length 5 because there are 5 processes in the system. Now here you can see that resources are allocated to all processes, right? P1, P2, P3, P4, P5, right? So here resources are allocated to all processes. So at every index in vector finish we will set the value false, right? We will set the value finish I equal to false for all I equal to 1, 2, 3, 4 and 5, right? And how this work vector is initialized? To this work vector we will assign the value of available vector, right? Now the second step, in second step we have to find an index which will satisfy these two conditions, that finish I is equal to false and ith row of request is less than or equal to work, right? Now see what is the value of work vector. To it we have assigned the value of available vector. The value of available vector is at index A is 0, at index B is 0, at index C is 0. So this value is assigned to work vector. So here you can see this is the value of work vector. At index A is 0, at index B is 0, at index C its value is 0, right? Now we have to find an index I, right, such that finish I is equal to false, right? And ith row of request matrix is less than or equal to work vector. So initially for all indexes, right, for all indexes I, the values in finish vector is false, right? So we need to find a row in a request matrix whose value is less than or equal to work vector. We need to find a row in a request matrix whose value is less than or equal to work vector. So here you can see that first row and third row, right, they satisfy this condition, right? So we will consider the first row, right? We will consider the first row of request matrix. So we have found this index 1, right? So this index 1 corresponds to process P1, right? So what happens, this way index 1 satisfies both the conditions. You can see that first row of request matrix, that is request 1, it is less than or equal to work, this condition is satisfied. And finish 1, it is also false, value at index 1 in finish vector is also false. So what we will do in this case, if both the conditions are satisfied, we go to step 3. So in step 3 what we do, we will update the value of work vector, right? So to work vector we will add the first row of allocation matrix. First row of allocation matrix is 0, 1, 0. So we will add 0, 1, 0 to work vector. So we will get new value for work vector 0, 1, 0. After that we will set finish 1 is equal to true, right? So at index 1 in vector finish we have set the value true, right? So after that again what we need to do, again we have to go to step 2, right? So in step 2 again we have to find the index which will satisfy these two conditions, right? So you can see that now we have set at index 1 in a finish vector the value true, right? We have set the value true at index 1 in finish vector, right? Now we have to find the index which will satisfy the two conditions which are specified in second step of algorithm. So here you can see this third row of matrix, right? You can consider this index 3, right? So you can see that at index 3 the value in vector finish is false, right? And the value of the is third row of request matrix, it is also less than or equal to work vector, right? Value of work vector is 0, 1, 0, right? So in this case what we will do, we will update the value of work vector. To work vector we will add the third row of allocation matrix. Third row of allocation matrix is 3, 0, 3. So to 0, 1, 0 we will add 3, 0, 3. So we will get new value for this work vector 3, 1, 3. And after that we will set finish 3 is equal to true, right? So at index 3 in finish vector we will set the value true, right? Then again we will go to step second of algorithm. And so now consider the index 4, right? Now see that in finish vector at index 4 the value is false, right? And you can see that fourth row of request matrix, right, its value is less than or equal to work. It satisfies this condition, its value is less than or equal to work, right? So since both the conditions are satisfied, we will consider the index 4, right? So after that, what we need to do, we need to update the value of work vector, right? So in work vector, we will add the fourth row of allocation matrix. Fourth row of allocation matrix is 2 1 1. So in this work vector, when we add 2 1 1, so the value of work vector will become 5 2 4, right? And after that, we will set the value in finish vector at index 4 to true, right? We will set the value at index 4 in finish vector to true, right? Now again, we have to execute the second step of algorithm. Again, we have to find an index which will satisfy both the conditions which are specified in second step of algorithm, right? So we need to find an index so that at which the value in finish vector is false, and that index I we have to find out, so that the ith row of request matrix is also less than or equal to work, right? So here you can consider this index 2, right, because the second row of request matrix is satisfying the condition that it is less than or equal to work, and in second index at finish vector the value is false, right? So we will consider the second index, right, because it satisfies both the conditions of step 2, right? So you can see that second row of request matrix is 2 0 2, right, and its the values of work vector is 5 2 4, 5 2 4. So here you can see that this condition is satisfied, that second row of request matrix is less than or equal to work, right? And it is already clear that value at second index in finish vector is false. So in this case, we will execute the third step of algorithm. We will update the value of work vector. To work vector, we will add the second row of allocation matrix. Second row of allocation matrix is 2 0 0. So to work vector, when we add 2 0 0, the new value of work vector is 7 2 4, 7 2 4. After that, in finish vector at index 2, we will set the value true, right? Again, we need to find the index I which will satisfy the two conditions which are specified in step 2 of algorithm, right? So here we will consider the index 5, right? So because at fifth index, right, at index 5 in finish vector the value is false, and also the fifth row of request matrix satisfies the condition that its value is less than or equal to work, right? Now you can see that value of work vector is 7 2 4, right, and the fifth row of request matrix is 0 0 2. So it satisfies the condition that its value is less than or equal to work, right? And also in finish vector the value at index 5 is false. So what we will do, we will update the work vector. To work vector, we will add the fifth row of allocation matrix. Fifth row of allocation matrix is 0 0 2, right? So when we add 0 0 2 to this work vector, we will get this new value of work vector 7 2 6. And after that, we will update this finish vector, right? In finish vector at index 5, we will set the value true, right? And then again we will go to step second of algorithm. So in step second of algorithm, we have to find an index I such that at index I in vector finish the value is false, and ith row of request matrix is less than or equal to work, right? So now what happens, now we cannot find any index like this which will satisfy these two specified conditions, right? So what we need to do here, now we have to go to step 4, right? So what we do, we go to step 4. In step 4 we check that whether in finish vector at any index the value is false, right? So here the finish vector is of length 5, and you can see that at every indexes the value is true, right? So here in finish vector we have not found any index where the value is false. It means the system is not in deadlock state. It means this system, right, is not in deadlock state. If we find the value false at any index in the finish vector, right, then it means that the system is in deadlock state. Here at any index in finish vector we have not found any false value, right? All the values are true, so the system is not in deadlock.